give a quick walkthrough the Ngram models. It's not the full set of slides, but we'll see someone's typing. This is a shorter version. Basically, this is just a shorter walkthrough. Not everything is in this one, but because we never had that lecture, I would like to at least once go through this material and see if everything is clear. Okay. So yeah, basically, I'll figure out what's going on. So yeah, today we're just going to briefly talk about this material again, and next week we're going to move on to some material on sequence modeling related to part-of-speech tagging. These will be Markov models, hidden Markov models, and we'll so Ngram modeling is to some extent related to this. In that Ngram modeling is also already a kind of poor man's sequence modeling in a sense. Okay, so oh, Nikolai, you're logged in twice. I don't know if you realize, but let's start. So we already talked about Ngrams earlier when we talked about text representation. So you might recall that at that time we said Ngrams are sequences of items from a sample, of n items. That's why they are called Ngrams, and these items may be units of any type. These may be. Sorry about this. I have to check what's. Oh no. Okay. If you hear weird noises, I'm sorry. These are misbehaving animals. These items may be of any type. This in our case, of course, we are interested in linguistically informed units, so in linguistic units. But an Ngram is an abstract structure, so it can be unit of any type. In our case, of course, we have units such as phonemes, letters, or characters, words. Where these words may be verbatim words, or these may be pre-processed words. We talked about stemming, for instance. So these may be Ngrams of stemmed words. And here's an example of character Ngrams for the string from the previous slides, Allen Mathison Turing, unigrams of characters, bigrams of characters, 4 grams and 5 grams of characters. This is rather self-explanatory. In language models, we are rather more interested in units at the level of words. So here are the word Ngrams for the same string, Allen Mathison Turing, at the level of words. Unigrams, the same, bigrams and trigrams. But in general, Ngrams may be of any order, including up to sentences. So you can consider Ngrams of sentences, Ngrams of phrases. There is also a generalization of Ngrams with which allow gaps between those units. So, for instance, some intervening material here, we might talk about them later when we talk about embeddings. Okay, so related to Ngrams is a question of whether we can somehow predict the next word based on some words that we've already seen. So the general question here is given, the general problem formulation here is given some history. Can we predict the next event? And Ngram models or language models, for the case of the Ngrams being linguistic units, are exactly these kinds of models. Based on the previous n-1 words, can we predict this language model will be trying to predict the next word based on some data. So here are some examples. This is rather easy. Once upon a, if you were to guess the next word in English, probably the very likely word here is time, because this is a phrase, a fixed phrase from fairy tales. For the second example, although it might sound counterintuitive, most of you will recognize that this is the beginning of a rather well-known song. So even though there's many things that might be done in the future, if you use the habeas corpus, more often than not, you will probably conclude this sequence with something like rock and followed by you. So even though here there's not much, there's a lot of options that could follow, a lot of actions that could follow this future tense. The highest likelihood action continuation would probably be based on this one specific rather famous lyrics. That is rather frequently represented in the web if you were to use the habeas corpus. Similarly here, please turn your homework, and what you most likely predict for the continuation here in English is the preposition in, because the phrase turn in homework is again a type of multi-word expression, turn something in, and it's a phrase that's very often encountered. So it's rather easy to predict this next token. Of course, it could be something else. Please turn your homework as soon as. Well, maybe not in this example. Okay, I'm running. I'm just. This is not a likely example for well-formed English. Okay, the most likely continuation is clearly in. So language models are basically statistical models of linguistic sentences, of sequences of the type of engrams, of a shape of engrams, where engrams are sequences of consecutive sequences of words. Of course, in the general case, we talk about the end being the whole sequence, the whole language as such, right? Why are they interesting? Why is it interesting to study such models? Why are these models useful in NLP at all? They have many applications. Most of you have already encountered many of them, probably. Predictive typing is one. So predictive typing on cell phones, predicting the next character based on the prefix you've typed, predicting the next word. Based on again on the previously typed text. This is also a feature of many cell phones that propose the next sequence of words for some fixed phrases. Also, we might want to assign probabilities to sequences of items, for instance, to be able to tell, okay, this is a more likely a valid sentence than this other one, if it has a lower probability, for instance. Engram modeling is also very frequently used in speech recognition, precisely for predicting the word sequence based on phoneme sequence. And we'll get to HMMs next time as an even more advanced technique. So engram models are very frequently used nowadays. It wasn't always like that. Well-known linguist Noam Chomsky in the late 60s stated that the notion of a probability of a sentence is an entirely useless one, and under any known interpretations of the term. So there was a lot of skepticism about using these kinds of probabilities, predicting word sequences and the probabilities of word sequences to have any application or any valid cognitively justified cognitive justification. This is not the case anymore. And it's shown even in cognitive science experiments that these kinds of predictions, continuations, are an example of a task that shows that in the mind we store something that might correspond to, what you could say corresponds to engrams, even if they are not well-formed structures. Another application that is mentioned here is, of course, spelling correction, grammatical error correction. I already mentioned that. Okay, so let's briefly look at what these engram models or language models are. Like I said, the general problem is that we would like to compute a probability of a word, some word W, given some history, so some previous words. Let's call this history H. So we'll have a probability of the word given its history. So how can we do it? Well, like the most coarse-grained approximation would be to estimate the probability from, in a standard way, from relative frequencies. So we take a large corpus and count the number of times we see that history, that what precedes the word, and count the number of times this history is followed by that specific word that we're interested in. And that's how we calculate this coarse-grained probability estimate. So for instance, for this sequence, its water was so transparent that the probability that it's followed by the would be expressed in the following way. Probability of the, given the history, its water is so transparent that, would be the count of this string where the prefix and the word of interest is included, divided by the count of the prefix. So it's a kind of relative frequency. And this works in a lot of cases, but there is an obvious problem. Of course, we can only estimate these counts based on some corpus. The corpora that are available now are really large, in particular corpora based on the web. So in particular, the full web being used as corpus. So very likely, a lot of language is already represented in such data set. Still, if you remember that Zipf's law and Heap's law, you might recall that there's never an end to this development of the vocabulary. Remember the Heap's law and the vocabulary growth curve? We said that due to certain, to some extent, anomalies in the language, to some extent, creativity in the language, there are always new words that can be encountered. And this will be a problem also here. If we just want to use the counts themselves, at some point, we will hit on a word that is not in the corpus, and our count will not be available. We won't be able to calculate the count. So some of these sequences will have 0 counts. So what can we do with this? Instead of using counts, we will do something very intuitive rather in this case. We will be computing probabilities of sequences of words. So here we are notation. This is a sequence of n words, W1 to Wn. I will be sometimes using this kind of notation. This is the notation that you'll be familiar with from most NLP books, 1 to n. This is also what's used in MATLAB for vectors. So if you remember how to decompose this kind of joint probability, this is a probability of a sequence of events, x1 to xn. This is the general case. We can decompose it using a chain rule to estimate this joint probability by multiplying a number of conditional probabilities. So here they are multiplied out. Probability of the event x1, then x2 given x1, x3 given x1 and x2 preceding it, and so on and so forth. And finally, the last event given the whole history from 1 to the... I'm sorry, I will... Sorry about this. I'll show you the culprit, so that you don't think that I'm making it up. the culprit. Now go. Okay. So we're multiplying out these conditional probabilities. So we have a product of the conditional probabilities. In the full case, of course, we have the conditional probabilities of the final event in a sequence, given all the preceding events in a sequence. So for words, we can write it out as follows. Probability of the word from 1 to n, the whole sequence of n words, would be the probability of the word 1, then probability of the word 2, given that W1 was preceding it, then probability of W3, given that 1 and 2 were preceding it, and so on and so forth, until we get to this final product where we have the probability of the final word in the sequence, given the whole sequence of the preceding elements. So this looks like this is a valid representation of this model. The problem here is, though, that we have this big tail of, or rather, this big head, long head of the entire sequence that's preceding the currently estimated final token. And again, some contexts might have never occurred before. So some of those contexts, if we see for a new sequence that we are trying to calculate the probability of the next word of, might not occur in the corpus. So this is where a certain simplification and a certain assumption comes into play. Namely, we're going to, instead of computing probability of the sequence of words based on the entire history, we're going to take an assumption. This assumption is known as Markov assumption. We're going to assume that the probability of words depends only on the previous word. So that we're going to cut off the whole head of that history and look at only the preceding element. This is a huge simplification, of course, and for many cases, especially in language, it will not work. But we can also extend this simplification a little bit and say it doesn't depend only on the previous word, but it might depend only on the 2 previous words or 3 previous words. So something similar to related to our n-gram notion. Can you think of a linguistic phenomena or linguistic contexts? You already have seen some of them in previous lectures, in which this Markov assumption is not valid. Just give some examples. That the next word depends only on the preceding words. The preceding word, previous word. Even from last lecture, you have examples. Longer text where subjects appear in the beginning and a reference at the end again. Yes, this is at the level of sentence structure, at the level of syntax. Indeed, some, especially in languages such as German, you have, for instance, this phenomenon of some verbs, particle verbs, being split such that in certain positions the word, the verb, the subject appears in the beginning, then there's the verb, and then there is the other part of the particle verb. So this is an example, maybe not subjects, but with verbs. So this particle verb doesn't depend only on the preceding, this particle part of the verb doesn't only depend on the preceding token before this particle, but there may be a lot of intervening material. But there is an even simpler example at the level of parts of speech. So parts of speech, if you remember, represent word classes. And it's not always the case that you can predict the next word because there is not enough based on the preceding word, because there is too much ambiguity and about what types of parts of speech might follow the current word. So already at the level of parts of speech, this Markov assumption doesn't hold, because we'd need effectively more context to be able to, for many cases, guess the next word correctly. And of course, at the level of lexicon, the most basic level, a lot of things can follow after every word, right? So this Markov assumption is a gross simplification in case of language, but it works in many practical applications. And a class of models, probabilistic models, based on Markov assumption, which those models will assume that a probability of a future event or a future unit can be predicted without looking into the whole history, without taking into account the whole history, is called, this class of models is called a class of Markov models. Like I said, this history may be really a short-sighted history of just the previous word, but it may be a bit of a longer history, such as the previous two words. So this is the case of a previous word. The next word depends only on the previous word. This is a bigram model. You at a time consider only two words together, the word you're predicting and the word that's preceding it. But in general, this is a class of models based on n-grams of arbitrary order. So you might take more than just one word, but anything that is hopefully not as long as the whole history preceding the given word. So now, using our previous representation of this decomposed probability into a product of probabilities, we can modify it given our assumption. So now the probability of a word sequence from 1 to n can be, we'll say it can be approximated by a product of probabilities of the given word, a word we're trying to predict given the previous word. So we're only taking into account the one context of length 1. So this will be our model, basically. This is all that's to language modeling based on n-grams of various order. We talk about language models of various order. Now let's think about how to estimate these probabilities. Again, going back to our most coarse-grained approximation, we can approximate this probability using counts. This will be this is known as maximum likelihood estimation. These counts we take from a corpus. The larger the corpus, the better, of course. The more counts we have, and we normalize it by the sum of all counts. Here again, so this corresponds basically to our normalized frequency, as we in one of the first slides talked about the relative frequencies. This is a coarse-grained estimate and suffers from the same problem as the one that we were talking about in the beginning. Basically, some of those counts we will not have in the corpus; they will just not be represented. So, but let's simplify it once again. And say that the probability of the bigram-based language model will be a count of the bigram appearing together, so the sequence of the preceding word following and the word we are estimating following it, giving the count of the previous word only. So the count of bigrams you can You can think about it yourself. Sum of bigrams starting with some word must be equal to the count of that word. So if you think about it, it can be simply this sum here can be simplified to this count. So this will be our new estimate for a bigram model. Like I said, it suffers from the same problem. But nevertheless, we'll get to the estimates in a moment. And I'm sorry, my voice is already becoming worse and worse, as I was suspecting it would earlier this time, unfortunately. For the exercise, there are some practical issues that have to be taken into account when building n-gram language models. First of all, most n-gram language models are built based on n-grams of order of known magnitudes or orders known to work well for most languages, and these are trigrams, 4grams, or even 5grams. Of course, there is research that uses n-grams of higher orders. I've seen papers that use n-grams up to 17 words. This results, of course, in very sparse estimates for some of those 17 grams. But if the data is large enough, and it makes sense and it shows improvement in the model, why not? There are some practical issues related to implementation. In order, if you think about this n-gram model, you might want to predict the first word. So we have so far been talking about predicting the last word in a sequence. Well, if we want to compute a model or somehow compute the likelihood of a sequence, we have to multiply out probabilities of individual words. So there is a situation in which you have to also compute the probability of the first word in a sequence, and the last word in a sentence being the last word. For that purpose, we introduced typically a kind of dummy tokens or pseudo words. Sometimes they are referred to represent start of a sequence, so that this S here will be a start of a sequence, and the first word in a sentence will be then represented as the word we are predicting given this start token. And we are also want to predict how sentences end, probably, and we will represent that by adding this end of sentence pseudo word, and say, okay, calculate probability that this is how sentences tend to end. Using the pseudo word at the as being the token to be predicted based on the final word in the sentences. Of course, for higher order n-grams, we will need correspondingly more of those pseudo words. For instance, for trigrams, we will want to predict the first word given, so that we have a trigram at the end, not bigram, to pseudo tokens that start it. So these are technicalities, but these are needed for implementation. What are the problems with those estimates? If you look at the formula that we were using, we are estimating the probability by counts. And these counts are taken from a corpus. So the first problem, of course, is that these maximum likelihood estimates, any count-based estimates, depend on a training corpus. Depending on what corpus you take, what genre it is, how balanced it is. If you remember the lecture on corpora, how to build a good corpus, what kind of properties it should have. Depending on what corpus you pick, how large it is, and what properties it has, the counts will be different, of course. So some words from historic data, for instance, if you were to estimate it, some probabilities of historic words, historically used words, historical themes, if you were to estimate it on modern data, of course, you will get counts of most likely 0 for some Shakespearean words, for instance. the same the other way, right? If you were to calculate modern words using historic data, you will get some counts of 0. So there is this sparse data problem, and this has to be somehow dealt with. The key problem here is can be pinned down to one problem: unknown words. There are some words that will be unknown in the corpus, and for those either non-occurring words or rare events that result in very low probabilities, we'll have methods of dealing with them, and these will be smoothing, discounting, and resorting to lower order n-grams. I'll get to that in a moment. But first, let's think about, okay, we've built this model, we have a corpus, we've estimated probabilities, we somehow want to know, is this language model any good? And what would it mean that a language model is good, that our sequence probabilities are good estimates of an actual language? So the main question here is how to evaluate these language models. Of course, the best, somehow, objectively speaking, in the context of an application would be what is known as extrinsic evaluation. This would be an evaluation of such a model in an actual application. So you take an end-to-end system, let's say a spelling correction system, you build a character n-gram model, and you evaluate user satisfaction using the system, for instance. And how many times the user picks the first word that the model predicts, right? The user will actually use the spell checker, let's say for a cell phone, and the first correction is the one that the user picks. That is the one that was meant in that context. This kind of evaluation, of course, would be the best for practical applications, but for actual real life, or let's say deployed applications. But more often than not, then these setups or building such an end-to-end system is logistically difficult. And in the context of research, this is rarely done other than for small-scale demo projects. And more often, a different approach to evaluation is pursued. This is known as intrinsic evaluation. Intrinsic evaluation is about measuring the quality of a model independent of any application. So there is a set of measures that objectively try to quantify the goodness or the quality of some model, based on criteria that we deem are appropriate for evaluating such a model. And in the context of our lecture, I will be, of course, talking about the second case, the intrinsic evaluation, rather than the extrinsic evaluation, which is a completely different scenario. So in the context of intrinsic evaluation, there is a certain setup that we usually set for in the evaluation phase of the model building. And the key part of this evaluation is building a data set that consists of a part on which the model is trained and another part on which the model will be evaluated. If you evaluate the model on the same data as the data that the model has been trained on, then of course the model is good because the model is being tested on what it's seen. So such an evaluation can be done, of course, when a dedicated procedure that accounts partially for the fact that this model is tested on training data can be pursued. These approaches to evaluation are called cross-validation, where part of the training model, typically in the scenarios where not a lot of data is available, part of the training data is split to act as a test set, and part of that training data, the other part of the training data, is used as a training proper, and in the specific portions, and in a cycle of reevaluations of model, a different test data is sampled each time. So in this case, effectively, some data always ends up being in either training set or test set. So this is not a proper scenario where a model is tested in a situation where it's never seen and some data. And this is what we would like. And this scenario can be achieved in a proper train test, so-called train test scenario, where a portion of a corpus is set aside and never looked at. Whoops, sorry. I don't know if you can actually see it, that it's enlarged, but something got zoomed in. A portion of a test set is set aside for evaluation, in the sense of data that has never been seen to the model. You never, even the experimenter, the developer of the model doesn't look at this data in order not to get biased. So this will be called blind sets. Very often it's also referred to as a held out set. This is truly unseen data. Still, you may want to experiment a little bit. So you set aside another portion of the data, smaller than the training set, of course, also, on which you tune the model so that the parameters are set to those performing best. So you train a model, test it on the test parameters on the development set, and tune those models so that the evaluation on this one portion of a test set is best. And then such a model would be evaluated on a truly unseen data, the so-called blind set. Now, is this clear? Is this procedure with train and test data clear? And the reason why, yeah, okay, good. If something's not clear, just tell me. Because like I said, I'm feeling a little ill today, and maybe I'm not making myself clear. Okay, I'll wait for your questions. Yeah, okay, good. If it was explained in another course, that's good. Probably machine learning. If you've, some of you have been in the machine learning course, it must have been introduced, this notion. Yeah, exactly, in machine learning. It's the same procedure. And then in machine learning, this cross-validation type of evaluation is maybe more frequent, especially in projects where data is hard to get. I will explain this notions of evaluations and creating test and training data and cross-validation. I will explain that once again at the end of the course when we come back to corpora. Well, at the end we'll also once again talk about corpora, and these experimental methods will be explained. Upload these updated slides. Yes. Upload these for text representation. You mean the slides that are here now, right? Today's slides, right? Yeah, I will do that. Yeah, this slide deck is part of, in general, language models. The extended version is also part of the text representation section, because n-grams and these n-gram models are kind of representation of text. Okay, so now that we know how to set it up and the procedure for evaluating a model, we can think about measures that would tell us something about those language models. And a very frequently used measure for language model is a measure called perplexity.
Perplexity comes from the English word, stems from is related to the participle be perplexed, which means something like surprised. And what it is if you look at the perplexities defined here, so what we have here is basically the probability of the sequence of words here in the inverse. This is squared. So it's a kind of normalized inverse probability, and this is calculated on the test set. So if you remember, test set is that data that the model has never seen. So using this inverse probability, we can gauge some knowledge about what the model learned from the training set and how, in some sense, the test set is different from the training set. So the high probability of the test set means that the model is not perplexed, in a sense, in a common sense of this word, surprised in a sense, by this new test set. So it knows the language well. The training data was either very representative, the training set was representative, or it didn't differ that much from the test set. And since we are taking an inverse here, inverse probability, basically in practice it means that the lower the perplexity, the better model. So high probability of the model means that the model is not surprised, but inverse would have an inverse probability. So the lower this value, the better the model. And this is related to different measure that is also frequently used in relation to language models, and this is cross-entropy. This notion might be also familiar to you from information theory, from theoretical computer science, I guess, from information theory. And cross-entropy encodes basically it's related to quantifying information in a channel, and it represents the average number of bits or storage needed to store information on a in a variable. And in the case of language models, this is done based on estimated distributions from a corpus. So these probabilities and cross-entropy in the case of a language model will take into account probabilities of a word sequence. This W here is a word sequence. This is spelled out here as a joint probability of this word sequence, and otherwise cross-entropy is calculated in the usual way. So it's a log at the base of 2. Typically, the base can be different than 2, of course, of this joint probability. So you can think about it as the average number of bits that are needed in the context of our in our linguistic context, the number of bits that are needed to encode each word. And perplexity, if you remember that formula, that previous formula, we have that same here probability of that sequence here. The perplexity would be, if you take a logarithm in the base 2 here, it would be 2 to the power of this cross-entropy. And you can check that by bringing this 1 over n to the into the logarithm, this context into the logarithm, and transforming it. You can check that this will amount to the same. And perplexity on that interpretation is the average number of words that can be encoded using this number of bits that are represented by this cross-entropy. So there are two interpretations kind of perplexity of a language model. And both are equally good measures of language quality, language model quality. Okay. We also, I'm sorry, my voice is already somehow completely going, and I think I will have to pretty much stop at this point, because my My throat is really hurting, actually. We also, maybe I will come back to this in the beginning of next lecture. Maybe I'll finish in the beginning of the next lecture before I get to HMNs. Basically, the last problem, and this is what was your task in the tutorial, also in the lab class, is the problem that we mentioned earlier of dealing with these unknown words, also known as out of vocabulary word. This is what it means here. OOV often represents out of vocabulary words. So the words that have not been seen because they are not in the corpus. If you want to predict the next word that's in a test set, and you want to evaluate this model in a test set, well, it may very well happen that in a test set there will be a word that you've never seen in a training set. So what to do then? And there are different ways of dealing with this problem. The main two related methods are smoothing and discounting. Discounting is a kind of, can be thought of as kind of smoothing. Basically, in both cases, we're going to modify these probability estimates. So we're going to basically hallucinate some of those probabilities and change them. The most basic type of estimator of this type, smoothing estimator, is so-called ED1 smoothing, or Laplace, also known as Laplace smoothing, introduced. And this consists of just adding 1 to every probability. So we're just going to hallucinate those probabilities. You can also add some other number to the probabilities. And discounting is the counterpart of adding probabilities. In the discounting, basically, we're going to lower some of those non-zero counts to assign later some probability mass to the zero count. So as soon as we encounter a word in a test set that we haven't seen in the training set, we're going to assign some small probability instead of that zero probability. And in order to account for that, in order to return that fake or hallucinated probability for those out of vocabulary words, we're going to discount all the other probabilities by some small number. So this is smoothing and discounting. Third method, I'm sorry, my voice is really like kind of ridiculous now. The third method is back-off method. And that consists of using basically less context. If we don't know a trigram probability, maybe we know a bigram probability that includes the words in question. If we don't know bigram probability, maybe we know at least a unigram probability. So instead of a trigram probability, we're going to resort to a lower order n-gram, and instead use the lower order n-gram probability in place of the missing value for the higher order probabilities. There's also another method called interpolation, which is basically a kind of combination of this back-off and smoothing. I'd say the most advanced technique. But in many applications, actually, advanced smoothing is sufficient, completely sufficient. I'm sorry about this. I think I will have to finish for today because my throat is really, it's really hurting me at this point. Are there any questions? We're going to continue this lecture, the remaining slides, the remaining part of this overview in the beginning of the next lecture. Next lecture will be basically head Markov models. So some sequence modeling for what we talked about last time, word classes, part of speech tagging. Are there any questions so far? I will put these slides also in today's I will make a link to today's session and put those compacted slides there. If there are no questions, then I would really very much appreciate if we could close for today because my throat is really gone and hurting me. So we'll start next week with the continuation of this. There is not much left. It's just a walkthrough of the smoothing methods, and we'll continue with HMMs. Okay, so we'll see you next week, and hopefully by then I'll recover. Yeah, for sure I will recover by next week. Bye.